Alright, one of the things we want to talk about is the anomalous behavior of water. Water is a very special compound, and there's lots of really strange and neat things that water does, or the properties that water has. So some of the important things, we're going to connect this to the kinetic molecular theory that we've been talking about. But according to KMT, substances should be less dense in the solid phase. We talked about that, right? We saw the diagrams. As motion decreases, then the attractive forces between these particles start to take over a little bit, and they come closer together and start to pack densely in the solid form. And with water, we talked about this last class, that water arranges itself in a special way using hydrogen bonding to align themselves, the water molecules to align themselves in such a way that actually the solid form is a little bit less dense than the liquid. It takes up, the molecules take up more space in the solid form because of how they're arranged. Water is proven to violate this typical behavior because ice is less dense. And again, this is due to hydrogen bonding, so just make sure you have this jotted down here. So solid water ice is less dense than liquid water due to hydrogen bonding, as I mentioned. The water molecules align themselves in a more rigid pattern that takes up slightly more space. Hydrogen bonding, the molecules align themselves in a rigid pattern that takes up slightly more space than the liquid. The other strange and neat thing about water is that water gets more and more dense as the temperature drops, which makes sense, but at 4 degrees Celsius is when it is at its densest. Okay? So 4 degrees Celsius is where water is most dense. And that is very strange, but it's very important for life on Earth. I mean, if you think about the lakes, okay, if water was typical, right, the lake would freeze from the bottom up. So you would have water on top and you'd have lots of ice on the bottom. And then the fish wouldn't be able to live, especially on the more shallow lakes when maybe it would all freeze over, right? But the 4 degree water, which is a little bit warmer than freezing, right? It's the densest. So at the bottom of a freshwater lake, the temperature of the water is 4 degrees Celsius. And as that temperature gets colder, it starts to rise, and then finally it freezes at the top. That's why in our lakes we have ice on top of the lake, and the fish can swim and be relatively, safe and alive underneath there. Okay, thank you. The question was raised here that is there an error in the first point, and there is. So all substances should be more dense in the solid phase. That's what I said, but I didn't type it. Sorry. Okay, as we continue, as the temperature drops to 0, as we mentioned here, density decreases until 0 degrees Celsius, at which point it freezes. That's why ice floats on water, and the water at the bottom of the lake is exactly 4 degrees. All right, now in your textbook on page 233, there's a diagram of that, and it basically looks something like this. In a lake, in the wintertime, on the surface we have a layer of ice, right, that floats on top, and 4 degree Celsius water is at the bottom, and then it starts to work its way up. And as you get closer to the top, it starts to get a bit warmer. It gets colder until you get to 0. Ice would be where it would switch phase. Okay? All right. So we're gonna watch a quick video on the strange and weird properties of water. So I'm going to just move over to that here. And I don't know if you'll be able to hear this very well, but we'll give it a shot here. I'll crank her up.
Here are 25 odd facts about water that might quench your curiosity. Cold water is heavier than hot water. 24. And hot water can actually freeze faster than cold water under certain circumstances. 23. Only 1% of the world's water is drinkable. 22. In Peru, there's a billboard that creates drinkable water out of the air. 21. doesn't actually conduct electricity very well, but the impurities found in water do. 20. During the Middle Ages, beer was consumed more than water because the alcohol was safer to drink. 19. Remember how I said that 1% of Earth's water is drinkable? Well, about 90% of that drinkable water is found in Antarctica. 18. 2/3 of the water used in an average home is used in the bathroom. 17. Drinking too much water can kill you. It's called water intoxication. 16. So, I said that 90% of the Earth's 1% of drinkable water is in Antarctica, right? Now get this. 20% of the remaining 0.1% is in a Russian lake called Lake Baikal. 15. It takes nearly 3,000 gallons of water to manufacture one pair of jeans. 14. The expiration date on water bottles is for the bottle, not the water. Although when the bottle expires, it may start to leak chemicals into the water. This, however, is usually not life-threatening, but might change the taste. 13. Bill Gates oversaw the construction of a machine that turns feces into drinkable water and electricity. 12. The reason that the machine works is that 75% of your feces is actually water. 11. People in Asia and Africa have to walk an average of 6 kilometers, or 3.7 miles, to collect water. 10. Your bones consist of 31% water. 9. Jellyfish are about 95% water. 8. There is more fresh water in the atmosphere than in all of Earth's rivers combined. 7. Because of the altitude, water boils quicker in Denver than in New York City. 6. The average American uses 100 gallons of water every day. 5. The average resident of sub-Saharan Africa uses about 3 gallons of water per day. 4. Water is the only substance to be found naturally on Earth in 3 states: solid, liquid, and gas. 3. If the sea level rose 10 meters because of melting ice caps, 25% of the United States population would be affected. 2. Scientists have recently confirmed that there is water on the moon. 1. Giraffes can go longer without drinking water than camels can. Enjoying our lists? Be sure to click that subscribe button in the top right corner so you don't miss.
All right, so shout out to list 25 here for our video. Okay. So any questions about the video or about the notes or about the properties of water? Anything in that video that was strange or interesting or questionable or anything that, in comments? Okay, good question. Good question. Does water boil faster or more readily, easier, at higher altitude or lower? I think I had this discussion with a student the other day. Oh, some are saying lower, some are saying higher. Okay. Okay. So what you need to think about, is atmospheric pressure. Okay. Now, when you are, think about this. When you're driving, and you drive through the Coppell Valley by Lumsden there, all right. When you go down into a deep valley, do you feel that the change in pressure in your ears? Anybody notice that? Okay, sometimes you'd notice that. Now, when you're going down lower, there's literally more atmosphere above you, and it's pressing down on you with a greater force. So if you think about water, when we start to heat water up and it approaches its boiling temperature, those water molecules are trying to escape out of the water into the air. So if there's less pressure pushing the water molecules down, they're going to jump to the gas phase quicker or more easily. So in Denver, it's a high altitude. That means there's literally less atmosphere above Denver. So there's less pressure putting down. So higher altitude is less pressure, lower boiling point for water. Okay? Now if you think that's weird, do you actually know that time passes at a different rate in Denver as it does in Because of the proximity to the center of the Earth, yes, this is like billionths of a second per year. But, yes, weird, hey? Pretty sweet. So anyways, back to water. Okay, any other questions? That was a good comment. Anybody notice anything else about the video that you have questions about? Or interesting to note about the beer one. More people drank beer than water because it was safer. The process of fermentation and that process of creating that actually got rid of a lot of impurities that existed at the time in the water that they couldn't filter out. And even if you think about in biblical times, when Paul told Timothy, drink a little wine, it's good for your stomach. So that probably would have been the same sort of thing, that process of creating that wine. The wine was, you know, better for you than some of the water that existed back then. You think about the impurities and the disease and stuff like that, right? So that's why, you know, that one was mentioned. Now, I don't think that more people drank beer than water, but it was considered to be safer in some areas at certain times. Yeah. You know what? Just different metals and stuff, really. Like, I mean, you think about. The question was, what kind of impurities would allow water to conduct electricity real well? If you think about water, naturally there are dissolved metals in water, really, like magnesium and you know, calcium and iron and stuff like that. The more dissolved metal that there is in water, the harder it is. So you've heard of hard water, right? So hard water has a little bit more of that metal in it, and it's not bad for you. But the softer the water is, or the more pure the water is, the less of those sort of ions are in the water. Yeah. Yeah. Question. Cold water is heavier than hot water. Well, if you consider, yeah, look at this diagram here, right? So this cold water here, it gets more dense. More density means there's higher mass per unit volume. So really, cold water is heavier than hot water, because hot water has more action. Think about the kinetic molecular theory. The molecules are bouncing around more, creating a little more space, so it's a little less dense. And with lower density, you have smaller mass for the same unit volume, sort of thing. So, yeah, good. Okay, any other questions before we move on about the video or the notes? All right. So 8.5 in your textbook, if you want to turn there to page 237, talks about heat exchange in mixtures. Okay, this is an important part of chapter 8 when we talk about transfer of energy. Okay, and heat exchanged. So there is a fundamental law of the universe called the law of conservation of energy. And this thermodynamic law states that energy in the form of heat, or whatever it may be, it's mostly heat, is never created out of nothing and can never be destroyed or disappear into nothing. It can only be transferred. Okay? This is called the law of conservation of energy. So if something is heating up, that means something else is getting colder. If you have a nice warm house and someone opens up the door in the middle of the winter, and all of you say, oh, don't let the cold in, right? Well, what's happening really is your warm air that you've got sealed in your nicely insulated house is now going outside. That warm air is going outside to try and heat up all of the cold air outside. Heat transfers, heat moves. And so when hot air goes out, the cold air rushes in to take its place. So it's not really cold air that's pushing in, it's the hot air that's escaping. Slight difference. But anyways, if something is being warmed up, something else is giving that energy away. Now the universe is a pretty big place, right? And energy also comes from, nuclear reactions, like we talk about the sun. Okay, there's some pretty massive energy that's given off by the sun, due to what we think is, anyways, nuclear fusion, nuclear reactions. So that energy is not necessarily beginning with heat. It's beginning with a reaction that produces this energy, and it's we see it as heat. Anyways, if someone has really cold hands, okay? Someone has really cold hands and they're trying to warm their hands up, and you grab their hands and help them because your hands are nice and warm, all right? Your heat is transferring to their hands when you're warming up their hands like that, okay? So heat is being transferred. It's not being generated. Even the friction, if you rub your hands together, right? Actually, why don't you do that right now? Just right now, put your hands together and just rub them hard. I bet you can't even do it for 10 seconds without it getting so hot. Okay? You see how hot that gets? Huh? Ah! It's burning! Anybody else still going? Huh? Okay, I'll put them to your face. It doesn't work for me because I have a beard. I can't really feel the heat. Yeah, you too. Your beard is massive. It's awesome. Are you keeping that beard or what? We just kind of got through No Shave November. Who? Oh, your sister wants to see it, so you're going to keep it on. Attaboy. That's the real man right there. Okay. All right, so are you creating heat out of nowhere? No, not exactly. Are you causing friction, rubbing actual, particles together? You're rubbing particles together? Yes. Is that generating heat? Yes. Is it coming out of nowhere? No. Okay, it's not just appearing out of nowhere. It's coming from somewhere. So these are things I want you to think about. Okay, so this law means, well, we talked about this. If one thing is gaining energy, then something else is losing it. And this is sort of the representation, mathematically or in a kind of an equation. So EH is like heat energy. So energy lost must equal energy gained. Sometimes it's easier to measure the amount of energy that something is gained than to measure the amount that it is lost. And sometimes it's even vice versa. But this formula, this little simple equation formula here, shows us that we only need to find one thing in order to know the other. So if we can determine somehow how much energy is gained by a certain object, we can tell how much has been lost by one or more other things that are connected to it. Okay. Measuring the exact exchange of thermal energy is called calorimetry. Calorimetry. Does anyone see a word in calorimetry that they recognize? Yeah, calorie. No, not metry. Calorie would be the one, probably. Nice try. Yeah, metry. Oh, really? Metry? You recognize metry? Okay. But yeah, C-A-L-O-R-I, and then of course if you had an E there, that would be calorie. All right? So when we're eating foods, when we're looking at, a diet or something, we count calories, right? Or you know that there's some kind of calorie content in the foods or the things that we consume. And that literally is, calorimetry is the process of measuring energy exchange, and calories are sort of the units of energy that foods possess. So calories. So if something has high calorie count, it has a high amount of energy. And nutrition is a whole other subject, but if you take in more calories than you're actually able to use, that gets stored as fat, right? So when people are on a diet, they be careful of their calorie count because they don't want to gain any fat. They want to use all the energy that they consume if you're on a diet. Now, if you're a sports guy or a sports girl, you have high-calorie diets because you're working real hard, because you're expending a lot of energy and your body literally needs fuel, right? So sometimes you need a high-calorie diet when you're working out or when you're, in the middle of a season or something, right? So I won't even begin to tell you what I used to eat when I was playing hockey down in the States. I ate about 5 times as much as I eat now, honestly, because I was working so hard. It's crazy. I could not even get through one meal that I ate down there. I could not even get through one meal. It would last me a whole day, maybe 2 days, honestly, one meal. Question? All right. So the energy in foods can be calculated. Now this here is called a bomb calorimeter. Yeah, that's right, bomb calorimeter. And what happens, let me just explain this diagram here. You guys paying attention here? Okay, look at this diagram up here. So this is actually how calorie content in foods is calculated, one of the ways. And we'll just go through this diagram a little bit here. Inside the the bomb, really inside this container right here, is a sample of food. It's a given mass of food, or of some kind of well, I guess food, whatever, something that might be consumed. And we have electricity leads that are kind of in here, and basically, once electricity is applied to it, basically they light it on fire. Okay, they burn it, consume it. There is oxygen in there so that it can burn, and what happens is the heat that is generated by this food or this substance, whatever it is, goes out into this part, which is the water. Okay, this red part, I don't know why it's red, but this is water that surrounds this little container. Okay, and there's a thermometer in here that measures the rise in temperature of the water. And so you can kind of see in this, with calorimetry here, the food, as it's burned, is giving off its energy, and the water is taking that energy on itself. And so, in this case, all you have to do is read the rise in temperature of the water, and you can figure out how much energy that water has absorbed. Okay? Now, how much energy has the water absorbed? Well, what we need to do is we need to go and study something called, here it is, thermal energy. Right? So let's talk a little bit about thermal energy. We talked about heat and the transfer of heat. A little bit of background here. And again, you don't have to copy all this down. I've underlined some of the important parts of my already summarized notes. So you can copy as much or as little as you want here. But I'll read through it and I'll highlight some things myself. So we use the heat. Yep. We use the word heat and cold quite frequently. Okay? In our everyday language, without them actually meaning too much. Okay? So hot, cold, what does that actually mean? One person may say cold, may call something cold, while another person right beside them might say that it's warm. Alright? So this happens all the time. If you meet someone, maybe you have a relative come in from Florida or something, right? And it's like 5 degrees up here, and they say, "Man, it's freezing," and you're thinking, "Well, it's November, or it could be minus 25 here. This is nice and warm, actually. T-shirt, shorts, right?" So both would be right from their point of view, because hot and cold is fairly subjective. Okay, hot and cold is fairly subjective. So what we need to do is we need to define hot and cold a little bit more clearly, and that's why in science we talk about thermal energy. What we want to do is we want to look at the kinetic molecular theory. We realize that atoms are in motion, and we've already learned this, right? Temperature. It's the average motion, or the average kinetic energy of the atoms or the particles that were measured. Right? You remember the definition of temperature from lessons before? Okay. If we heat a pot of water on the stove, what you're doing is you're taking electrical energy and you're causing the atoms in the element. Okay, so if you think about a stove, the stove element, a lot of stoves now don't have those black elements that are exposed anymore. But if you think about, that's what this example is talking about. The electrical energy causes the element to get hot because those atoms are now rubbing each other, like we just made friction, kind of generated some heat because of the rubbing together. So in a stove, those atoms are moving together and they're making friction, making heat, which causes their energy to rise. That energy and those atoms, they bump into the atoms of the pot that's on the stove. And so you have electrical energy causing heat to be generated because of friction. And that heat is transferred. We just talked about transfer of heat, right? So as the stove makes heat, it is transferred, given off to the pot. So that's when we heat a pot of water on the stove, that's what's happening. The atoms then in the pot bump into the atoms in the water, causing the water temperature to rise. The water temperature goes up. All right? So you would have to be able to explain this process starting from electricity, electrical energy, okay? The vibration of atoms, the transfer. Do you guys know how electricity works? Think back to your other science classes. If electricity is flowing through, electrical wires to these lights or to whatever we're powering here at the computer and so on, what's happening there? Anybody know? Anybody know? You guys know? No? What's electricity? Yeah? Pushing. Okay, what is it that's moving? What is it that's kind of traveling? There's something specific that's actually moving from atom to atom through electrical wires and stuff like that that's giving off energy. What'd you say? Yes, electrons. Electrons are being passed, okay, along, and they are moving and flowing, and they're giving off their energy. So electrical energy, electrons are moving at the basic atomic level, right, and causing other atoms to vibrate and to have friction, and then heat is now generated from this. Okay. So when we heat something up, we're actually transferring energy. So we talked about transfer of energy earlier in the class. Heat is then defined as thermal energy that flows from one object to another. And that is due to the difference in temperature. Right? Very important statement right there. That's what heat is. It's the flow of energy. The flow of energy from one object to another. And that's due to the difference in temperature. You don't have to push heat to get it to flow. It just does that automatically. Okay? There's a natural, law. Again, we're talking about thermodynamics. Okay? Systems of high energy. If you have high energy, that energy will want to travel to a system or to something that has lower energy, so that the energy is balanced. Okay? And that is transferring. That's energy being transferred is the flow of heat. Okay? So just by fact that if something is hot, it will start to cool down because it wants to give its energy to everything else around it that's not quite as high temperature as it. Okay? It's important to note that while we use the word flow, that there's not an exchange of matter. Okay? Flow does not mean there's an exchange of matter happening. It's an exchange of energy. There is not anything called like invisible heat carrying liquid or anything that flows from one to another. It's important to know this since at one point it was believed that there was such a liquid called caloric. That's where we get our term calorie from. But this was sort of a belief. There was actually something physical that was caused something to get hotter. Okay, so it's a flow of energy. Okay, so here's what we did. We rubbed our hands together earlier, right? And you can feel them heating up. Mechanical energy is causing a temperature change. So mechanical energy, that's the energy that's created by friction. Okay, when things are rubbed together, the temperature rises there. You rub your hands. Okay, even in a machine, right? If you have a machine that is working and the parts of the machine, they're moving and they're rubbing against each other, it will generate a lot of heat because of that friction. That's why oil is used in an engine, to kind of dissipate that heat and to make the less friction between the parts. That's why you spray, lubricants like WD-40 on inside your wrenches or locks or mechanical things, so that they can actually flow freely, because the friction generates heat and kind of gets corrosion in there and stuff. James Joule did a number of experiments with heat and temperature and was able to determine how temperature, mass, and energy relate to each other. So he was able to determine how temperature, mass, and energy relate to each other. And because of his work, there's a unit called the Joule, which is used to measure the amount of energy. So when you hear the word joules, That's a unit to measure energy, joules. And calories sort of is also a unit to measure energy. Joules is sort of the more international system. And this is what he came up with. This is what he came up with. This formula right here. Energy equals, and you just write this out, E equals mc delta T. Just write that out. The specifics of this are on the next page here. E equals mc delta T. Energy equals, anybody know what M might stand for? Mass. Very good. Anybody know what C might stand for? That's, you're looking ahead in the notes. Very good. Heat capacity, specific heat capacity, which we'll finish up this lesson talking about. And then delta T is, yeah, remember delta, Greek letter, means change in temperature. Okay, so here it is. E is energy, M, mass. Now, mass in kilograms is typical, and that's because the units for this constant we're going to talk about are generally in kilograms. Okay, so delta T is temperature. Can be Celsius or Kelvin because we're just talking about a change. And C is, and I'll rewrite this up here, E equals, you don't have to put the H there, mc delta T. C is called the specific heat capacity. Now, specific heat capacity is simply the amount of thermal energy or heat that is required to raise a certain mass of material, 1 kilogram, by 1 degree Celsius. So what this really means is that if you heat up two materials that have different specific heat capacities, if you heat them up at the same rate, one is going to change temperature quicker than the other. Okay? Some materials are very good at absorbing heat and not reflecting that in the temperature change. Like water is one of them. Water has a pretty high specific heat. And that is another factor, another property of water that's very special. Water absorbs heat very well. It can absorb a lot of heat energy before the temperature rises, which also means that water can give off a lot of energy before its temperature drops. So it can actually hold a lot of energy, which is very good for us here on Earth because our oceans and lakes and things like that absorb energy and give off energy whenever needed. There's large storehouses of energy in the oceans, which help our planet, along with the atmosphere, which help our planet to stay relatively consistent in temperature. So because of where we live, it gets pretty cold in the winter, pretty hot in the summer, but overall, Earth as a planet doesn't fluctuate in temperature from different spots very much compared to most planets, right? So that's a big part of it. In the summer, water takes a long time to heat up, a large volume of water. And in the winter, it takes a long time for it to cool down. That's what helps us stay relatively consistent. Okay, so this chart, you do not have to copy this down. You'll see this chart, I think, page 235 in your text. This gives a list of specific heats, and we are going to talk more and more about this as we move on, but this has already been a bit of a long lesson here. So the specific heats of different materials are listed here. And really quickly, okay, where's water? Water is here. So about 4,186, okay, joules per kilogram to raise it 1 degree Celsius or 1 Kelvin. So look at how high this number is. Super high. Compared to something that's quite a bit lower, like glass. Look at that. Glass and water. See that? So that means that if you heat up glass, it'll get pretty hot pretty quick compared to water. Or look at this. Lead is also really small. If you were to heat up a piece of lead, the temperature would rise just like that because it can't hold a lot of heat. Make sense? Okay. Now listen, this is a lot of material. You're going to need to go over your notes. You're going to need to read the text. Okay, 8.4 and 8.5. Read those. But anyways, we're going to kind of stop and turn our attention to maybe some questions. I'll do this example with you a little bit later, but this is an example where we can use this formula to calculate energy. Okay, so take a look at that, and yeah, that's kind of the lesson for today.